Hi, hello everyone. My name is Kabir, and the topic for our group was non-reciprocal geometric phase in nonlinear frequency conversion. So today I will be introducing what geometrical phase is, what Lorentz reciprocity is. I'll then build up what our system is, some notation and some dynamics of what is actually happening. Then Abe will continue and introduce what the non-reciprocity is in our system and some of the experimental results that were concluded in the paper. So let's start. So firstly, what geometrical phase is. So as you might all know, under the evolution via Schrödinger equation, our state gets a phase factor, which is the exponential minus I by h cut integral h dt. This is usually known as the dynamic phase under time evolution from the Hamiltonian. Now, in some scenarios, under cyclic evolution, we might also gain another phase. This phase is known as the geometrical phase. So, what do I mean by cyclic evolution? Suppose I have some parameters of my situation. I slowly vary these parameters and I bring them back to their initial value. Now, under this slow change of parameters, this is usually known as the adiabatic approximation. My state sometimes acquires an additional phase due to the geometric structure of the space. What do I mean by geometric structure? I'll explain this in the later slides, but for now we can understand, take the whole phase obtained and subtract off the dynamic phase. This is what we'll be using, and this is known as the geometrical phase obtained. Okay, so now there are many formulations of geometrical phase. Many common ones being Aharonov-Bohm phase or the Panchratnam and Berry phase. Now, the Aharonov-Bohm phase, some of you might be familiar with, is the one when if I have a charged particle in a four vector potential and it treated quantum mechanically, so it obtains a phase factor. When suppose I have a solenoid and I travel my charged particle around it, so it obtains a phase factor, which is a gauge invariant phase factor due to the topological properties of my space. So and that is a very common Aharonov-Bohm phase. There are other phases also like Berry phase, Panchratnam and Berry phase, and we will be considered with the latter ones for the most part. So you can also see the idea of geometrical phase as I mentioned from the geometrical structure of space. So suppose I start my vector at a point A pointing towards B and I go towards B, then I traveled slowly I move my vector towards C so that it always points towards the next point, and then I bring it back slowly to A. Now the key point to notice is here is that when it comes back to A, it's actually 90-degree rotated from its initial position. This might seem very astonishing because if I'm on a plane and if I do the same thing, I'll end up back where I was. So this idea is known as this idea of the phase that it has picked up is known as geometrical phase. What do I mean by parallel transport? It means that my vector is always following the curve on which it is. So if I did the same thing on a plane, on a sheet of paper, I'll end up back exactly on the same direction in which I started. But I don't on a sphere. Why so? Because my sphere has some intrinsic curvature in it. This is the idea of geometrical phase. The intrinsic curvature of my surface gives me a phase. Now, the abstract idea is that this surface with curvature, might be a surface in the space of parameters. So the geometrical phase is picked up because of the curvature in the space of parameters, not necessarily an actual XYZ space. So this was the key idea and it will be used later on when we plot the state vector. So moving on. As I mentioned, we'll be focusing mainly on the Panchratnam Berry phase. So we need a way to calculate this phase for arbitrary transitions from one state to another state. So Panchratnam gave this way to calculate the phase difference between two polarization states. Why do I call it polarization states? Because this phase is usually applied to the case of a light, its polarization vector. So even the polarization vector of light can be thought of in this way. Thus, as we change the parameters of the system, the polarization vector transforms on a sphere in some sense and acquires a geometrical phase. This is the idea of how geometrical phase comes into picture into optics and polarization. Cool. So this was the formula given for the phase difference between two polarization states on this sphere. Phi equal to argument of psi 1 psi 2 inner product. So the main point here is that this phi is not transitive. What do I mean by transitivity? So I'll go back to the previous picture once. So A and B, suppose I calculate the geometrical phase between them. Then I calculate between B and C, and then C and A. If AB and BC have the same geometrical phase, it does not mean A and C have the same geometrical phase. This is what non-transitivity means, and this will be useful later to get a more geometric intuition of how to get this phase, looking at this from the surface, especially for spheres. So using this, we can see that if the state progresses from psi 1 to psi 2, the geometrical phase acquired would be half the solid angle subtended by the geodesic triangle. What do we mean by this? So look at the A, B, C points. These subtend some angle at the center, right? And why do I call it the geodesic? Geodesic essentially means the straightest lines possible on a surface. Now you might ask why not it's just a straight line joining two points. So the idea is geodesic is the path which a particle under no influence from any other force will take, and it is the shortest length path on that surface. For planes, Euclidean planes, the geodesic are just straight lines. But for other surfaces, that might not be the case. That isn't the case usually when we have some intrinsic curvature in the surface. So for spheres, the geodesics are just the latitudes. So from A to B, this is a geodesic, C to A is a geodesic, and B to C is just an equator. So this whole geodesic triangle subtends some solid angle at the center of the sphere. We are claiming is that the geometrical phase acquired throughout will be half of this solid angle for polarization vectors. So moving on. Yes, so we can see clearly this credits go to some Cohen et al. They a very nice paper discussing phases, geometrical phases. So we can see clearly that when we project it on to the circle, uh, then the solid angle is 4 theta, but the phase acquired just by the polarization vector is 2 theta. So this is essentially why we were saying that the geometrical phase would be half the solid angle subtended by the geodesic triangle. Hope it's clear. So moving on. Now there's an essential concept of block sphere. If some of you might have noticed, I had marked it as some S1, S2, S3 and L and R. This is essentially the notation used for a block sphere in general. Now, what is a block sphere? It's a very universal concept. Whenever I have a two-level system, it can be represented on the block sphere, which is usually known as Poincare sphere in optics. So, what do I mean by two-level system? So we have a Hilbert space for a quantum system, right? And if it's spanned by only two eigenvectors, 0 and 1, then we call it a two-level system. Now, any two-level state can be put into this form because using normalization, the state is normalized. We assume that, so we can always put it in this form. But you might ask, why not some other form which satisfies the normalization? This form is particularly useful because, as you can see, we have these angular parameters theta and phi. So it intuitively gives us the idea of a sphere being formed. But there is a caveat here. So I'll not go into that. So because the total phase minus sign doesn't change anything, so actually it should be theta by 2, but that's not really relevant for our situation. So we'll just use cos theta and e to the power iota phi. Just the angles give in the form give us the coordinates on the block sphere. So this is some illustration. So actually there's a very interesting fact about this. So if I put in some magnetic field or something, or just leave it as it is, if I start with any state, it relaxes upwards towards the zero ket, which is kind of opposite to what we would usually imagine for a state. It falls down as it relaxes, but that's not the case on the block sphere. Everything is inverted in some different from mirror intuition. So cool. This is all the representation of the block sphere, and this block sphere is what we were using to depict the polarization states. So as you will see later on, as I progress in the presentation, our state vector for the nonlinear amplitudes can be represented on the block sphere. It is essentially an analogy to the two-level system, even though we are not doing any quantum mechanical treatment as such. So we can use the same techniques. So the other key concept, as I mentioned, was reciprocity. So having discussed geometrical phase, the next part is reciprocity for the paper. So reciprocity refers to a class of theorems, very widely ranging theorems, but we would be looking only at a particular subset of these theorems dealing with electromagnetic phenomena, and light also is an electromagnetic phenomena, but a particular class of that, the Lorentz reciprocity theorem. But all of these reciprocity theorems have a common theme. They relate inputs and outputs of a linear system to those of an identical system in which the inputs and outputs are swapped. So, Lorentz reciprocity describes a relationship between one distribution of current and resulting fields and a second distribution of current and resulting fields. This is particularly useful in very much experimental settings and also theoretical settings. So, and as we'll see, the breaking of reciprocity is what has become very useful in recent years. So, and some caveat here when both the scenarios take place in identical regions of space. A key point to notice is the linear matter. Linear matter is an important thing because we'll be breaking it by some non-linear system. So, and usually non-linear systems break reciprocity. So the reciprocity can be put into a more precise form in the following equation where E tilde, E tilde, J tilde are the time varying currents and fields of my system. So actually, the theorem from reciprocity is that E1 J2 minus E2 J1 is 0, the integral is 0. But for many cases, when J1 and J2 are disjoint current sources, we can actually put it in this form, which is sometimes much more useful. So, as you might notice, the volume integrals are over two different volumes, as I mentioned. For the cases of disjoint currents, we can write it in this form, and that's the case we usually deal with in experimental setups. So, but this is not the most general form of the Lorentz reciprocity. So moving on. So to get a more intuitive sense of what Lorentz reciprocity is, we can think of it in a circuital way. So if I have a two-port circuit, it is said to be reciprocal if the voltage V2 appearing at port 2 uh, due to current applied at port 1 is same as the voltage V1 when the same current is instead applied at port 2. So we are switching the ports, but our voltages remain same because we are switching voltages and currents both at the same time. It's kind of reciprocal. So moving on. Yes, so now I'll set up what our system is, what the geometrical phase in that system is. Then Abhay will, as I discussed earlier, will tell what the non-reciprocity in the system is. Essentially, as I mentioned, to break the reciprocity, we'll be dealing with a non-linear system. As was evident in the title, we are using nonlinear frequency conversion. So our frequencies are denoted by omega 1 for the pump frequency, omega 2 for the signal, and omega 3 for the sum frequency. So we usually have omega 3 equal to omega 2 plus omega 1. So we have used some approximations and notation. So the I just discussed what the approximations are. These are the ones we usually use and the notation that we'll be following. So the undepleted pump approximation, the amplitude of the pump A1 remains essentially constant throughout the process. Under this, we can write the electric field. This is the second approximation, the slowly varying envelope approximation. So we can write the electric field as some slowly varying function of coordinates times our phase factor, complex conjugate because well, our fields are real. And also for the sake of convenience to match with the paper, we redefine our amplitudes in terms as equation 5 as given. So, moving on. So in this equation, the dynamics can be written as equation 6 and 7. Kappa is the constant which depends on the pump amplitude. So we have taken it essentially to be constant since well we have the undepleted pump approximation. Now these equations just come from our Maxwell's equation and imposing the slowly way, the SVEA and uh, imposing that the second derivative is much less than the first derivative. Now the key step here is to see that we have two amplitudes A2 and A3. So whenever there's a 2 we can think of it in some sense as a two-level system. It's not exactly a two-level system as it previously was because the matrix entries depend on Z. So we have to go to a rotated frame, which is done in equation 8. Now in a rotated frame, the matrix is independent of Z. It's not a variable matrix. This makes it much more convenient to solve. We can diagonalize it, we can find the eigenvalues. And after doing everything, we go back to our normal frame by rotating back. Fine. So we have this matrix equation. This should also give you some idea about this also looks like the Schrodinger's equation in some sense, right? I have I d by dt psi equal to h psi, where psi is my state vector and h is the operator acting on the state vector. Even though I emphasize there's nothing quantum mechanical that we are doing right now, it is just the analogy, and that analogy is what we'll use further. Same analogy for geometrical phase also. Cool. So we start with the initial condition 1, 0, transpose just because it's a column vector. For this initial condition, the geometrical phase acquired, as I mentioned, is the total phase argument A2 tilde A2. The tilde ones are the rotated ones, minus the dynamical phase acquired. Now this dynamical phase, as I mentioned earlier, can be thought of as an analogy from the integral h dt. So z is playing the role of time in Schrodinger equation. So we get equation number 9, which is, as we see, which is exactly just the total phase of A2. So interestingly, the whole geometrical phase acquired by this two-level system is nothing but the phase of A2. And the analytical solution of A2 we already know, we have solved it multiple times in class. Putting that back in, we get the geometric phase acquired up to a till distance z. Cool. So this is the plot of the geometrical phase. So I'll discuss some interesting limits here. So as we can see, for delta beta equal to 0, when delta beta is denoting our phase mismatch, for delta beta equal to 0, whenever it completes a cycle, it picks up a phase of pi. I'll discuss this later from the block sphere point of view, but this is an important point. So we have maximum phase gaining for delta beta equal to 0. And the other interesting limit is when delta beta is much larger than kappa, mod kappa, sorry. So in this limit, there is no gain of geometrical phase. It's essentially close to the axis, as you can see the lower almost reddish line. So these two extreme limits are what we are concerned with. So essentially, you can start seeing the non-reciprocity here. In one direction, when we have very low phase mismatch, we have a very high gain of geometrical phase. And in the other direction, when there's a very high phase mismatch, there's a low geometrical phase. So there are some hints of non-reciprocal geometrical phase that we can see from just this figure also. And Abhay will elaborate more on this, on how to create this two opposing phase mismatches in different directions. Fine. So moving on, we can also depict the evolution of the state vector on the block sphere, as I mentioned previously. So on the block sphere, again the two important limits, the delta beta much larger than kappa 1, mod kappa is, as you can see, I think it's just a dot on the S1 as is expected. It has no geometrical phase essentially. So our trajectory on the block sphere is essentially a very small radius circle. So it subtends almost no geometrical phase. And the delta beta equal to 0, 1, it passes through both the north and south pole, and every time it passes, it gains a factor of pi. So these are two extreme cases which actually show the non-reciprocity. The key goal is to build a material such that it has this non-reciprocal phase mismatch. So thanks, that was all for what I wanted to explain. Now Abhay will follow up and show how the paper went towards getting a material which has this non-reciprocal phase mismatch. Thank you.
So, myself Abhay, and I'm continuing the part where Kabir had left. So, Kabir had already introduced this coupled differential equation and how to solve this coupled differential equation. And this is the value of the this is the expression for signal frequency. This cos gz plus I delta beta by 2c sin gz exponential minus I, here I is missing, I delta beta z by 2. So from now in this section we are analyzing for a particular crystal lithium niobate whose defect is given by 2.5 into 10 to the power minus 12 per millivolt, and the pump has frequency 1.11 into 10 to the power minus 10 to the power 15 radian per second, and the corresponding wavelength is 1700 nanometer. And there is a signal whose frequency is 1.57 into 10 to the power 15 radian per second, and corresponding vacuum frequency is 1200 nanometer. So in some frequency generation, we are creating another wave whose frequency is just the sum of these two frequencies. So it is 2.68 into 10 to the power 15 radian per second, and corresponding vacuum wavelength is 703.45 nanometer. And since every crystal has their dispersion relationship, so we can get back their wave wave vector from their corresponding frequency. Dispersion relation is basically the a function which correlates frequency and wave vector. So if we have wave vector, then we if we have frequency, then we can get back their corresponding wave vector. So for this omega 2, this crystal has this wave vector, this this phase, and for omega 3, that is 2.68 into 10 to the power 15 radian per second, the wave vector or phase is given by 1.95 into 10 to the power 7 radian per meter. And all we are analyzing this at the other end, that is at g equals 15 millimeters away from the origin. So if we put these values g d effective and beta 2 beta 3, then in kappa, which expression is given by minus 2 d effective omega 2 omega 3 a1 by c square under root beta 2 beta 3. We know beta 2 beta 3, we know omega 2 omega 3, we know d effective for lithium niobate. So we will get kappa as a function of a1, that is pump, amplitude of pump, and from there we will get the value of g, which is given by under root of delta beta square plus k kappa square by 2. So we know kappa, value of kappa, we just substitute it here, we will get g. And once we know the g, this expression which is written in argument is expression for a2, and there there is I missing here. So once we substitute the value of g here, we will get e2 as a function of delta beta mod a, because a is sitting here in kappa. So we will get a2 as a function of delta beta, that is phase mismatch, amplitude of pump, and z. But we know the value of z, that is 50 millimeter. We just substitute it here, we will get some expression for a2. And when we plot this a2 as a function of the pump amplitude, mod of pump amplitude, and this phase mismatch, we'll get this graph. And this graph is just a zoom version of this original graph. We are looking for a small delta beta, that is small phase mismatch. Here we can see that there is some periodicity, and also once we get the expression for A2, we can take the argument for this expression. Once again, there is I missing here, so some complicated expression for argument, and the plot of that argument as a function of phase mismatch and amount of A1, that is amplitude of pump, is shown here. This is the contour diagram, and again we can see here that for small delta betas there is some periodicity. You can see here, this is zoom version of this original graph. We are just looking for a small phase mismatch. So the next thing is, so the next thing is that delta beta is beta 1 plus beta 2 minus beta 3, that is phase mismatch. We know beta 2 and beta 3. The only thing we don't know is beta 1, which causes this big delta beta to vary, and this amplitude we don't know, just a strong pump, but we didn't explicitly put the value of this pump amplitudes anywhere, so we are considering this as a parameter or a variable, and these are the plots. So we get this thing. Also, Kabir had mentioned that this geometric phase is directly proportional to the argument of A2, which expression is given here, this expression. So we can see here that when delta beta is increasing, when delta beta, that is the phase mismatch, is large, we can see easily that this blue color is dominating, it is covering most of the part, and we can see here that that blue color is from the smaller range, means it it is just small values. So as the phase mismatch increases, the geometric phase will decrease, and this is also shown in this Poincare sphere. Here the this circular thing is representing the evolution, and which causes geometric phase, which is just half of the solid angle it makes at center. So we can see this is the case for delta beta equals 0, where phase is matching, this orange color. So here we can see that this has the maximum solid angle at center. Maybe this is making 2 pi angle at solid 2 pi solid angle at center. So its phase match, it geometric phase is pi because it is just half of the solid angle, and we can see this red point, which is delta beta. When delta beta is large, that is 100 times of kappa. So we can see here it imposes zero solid angle at center, means it has the least, it has minimum or geometric phase. This is only because it has this red color represents where there is large phase mismatching. That is why there is no any geometric phase, and geometric phase is just a constructive interference of many phases, and we know that phase mismatching is that waves have different phase velocities. So when when there is large phase mismatching, so they just destructively interfere and just cancel out the geometric phase. And in the case when there is less phase mismatch, that is delta beta goes to zero, these geometric phase will constructively interfere, and hence it will cause a large geometric phase. And also, so that's all. This is showing the significance of phase mismatching, that when phase mismatch is large, we are getting zero geometric phase. And so we are thinking of why we are talking about this geometric phase. So it is something related to non-reciprocal nature of the crystal. And the thing is, we are fixing the direction of pump. So here we are taking two cases. This forward case when light is that the signal is moving in the direction of pump, and the backward case when signal is moving in the opposite direction of pump. So if somehow we are created in forward case that delta beta is close to zero or equals to zero, that is phase matching, then when this signal, and if now now we suppose that now our signal is in considering the backward case where we have same pump in the same direction, but now we reverse the direction of signal. So if we have delta beta equals 0 or close to 0 in forward case, it need not to it need not be equal to 0 or close to 0 in the second case. And hence, if we have good phase matching in first case, that when signal A2 is moving in the direction of pump, we don't claim that we will get delta beta equals 0, that is phase matching in the other way, that is in backward case. So it is something related to direction, that when signal is moving in the direction of pump, we have good phase matching and getting good result, good A3, because our A2 is not self-focusing, it is only gaining by phase. But in backward case, since delta beta need not to be zero, because we are changing the sign of beta, so delta beta need is no more zero. So we are falling in the first case, we are falling in this region where delta beta is small. So we have some geometric phase. But as delta beta increases, this geometric phase destructively interfere each other and cancels down or goes to zero. So this direction of pump signal plays a significant role, and this is only that these papers talk about. that there is some non-reciprocity because this signal, once this signal changes the direction, the behavior of this crystal or the response of this crystal changes completely. Means in the first case, the forward case, it is working smoothly, but in the second case, because here delta beta is 0, but in the second case where in the backward case, this delta beta is not 0, so it may be that the signal it will start getting self-centered, then it will start accumulating at some point in the crystal because of some non-linear response of this crystal to this signal, which which leads to the accumulation of the signal A2. So this is what the Lorentz reciprocity or its significance is, that changing the direction of signal changes the property of crystal entirely. Now there is one more thing. This is completely based on experiment. This is omega versus beta, means that this is a two. This is a dispersion. This represents the dispersion relationship, or we can say this is a photonic band structure. And here, this blue line, and there is a red line. This blue line represents the horizontal mode when the light is in when light is horizontally polarized. Then this represents the this blue line represents the dispersion relationship between, that is omega as a function of the vector beta, and this red line is when light is vertically polarized. Then this red line represents the dispersion relation. So here we can see that how that we can't generate any omega 3 for a given omega 1, that we can see here, that once we choose a frequency omega, some frequency omega v on this curve, and we are trying to create a frequency omega 3 which is horizontally polarized, so we can't choose any photonic transition because there is some constraint on it, that if we are choosing this omega, this is some beta, corresponding beta, which is less than 7 into 10 to the power 6, close to 7 into 10 to the power 6, and another omega h, and has corresponding beta which is close to 9 into 10 to the power 6. So there is some constraint that the phase mismatch should goes to 0. Even a small deviation from this point can lead to change in phase mismatch, which is of the order of 10 to the power 6, which is large, and hence the light can't propagate. It will get self-centered in the crystal. So we can't choose any omega h for a given omega v or any photonic transition. So here it shows some selectivity. Means if we once we have choose omega v, there is some there may be some omega h for which delta beta is 0, and that is the only photonic transition that is possible. and that is all it about this graph represents. And basically what we are doing here is we have some pump which is vertically polarized, and we want to generate a horizontally polarized signal. So we are looking for the protonic transition, and this is just a cross section of a waveguide. And so here it is also mentioned here that where it is, more specifically we propose the photonic, yeah. So here it is mentioned that one can see the momentum matching condition can be fulfilled by choosing correct frequency of interacting waves in waveguide. Means we can't generate any frequency, any omega h for a given omega v. There is some selective. See, that momentum matching condition can be fulfilled. So we have to choose the frequency correctly, and this is the case we have already talked about, that when beta is greater than 0, this represents the case when light is propagating in the direction of pump. So we know this, that here if somehow we have managed delta beta equals to 0, that is phase matching. This is not possible in the other case, that is when beta less than 0, means when the signal is propagating in the opposite direction of pump. So this is all, and so what does this signifies? This signifies the importance of phase matching, that this selectivity represents that how phase matching is important, and phase matching is also there in reciprocity. So somehow they are related, that for the large phase mismatching, the geometric phase goes to 0, and this also represents the importance of phase matching arises due to the non-reciprocity nature of the system, that is phase matching in one direction but not in the opposite direction.